The goal of this video is to introduce the idea of intelligent agents, to give a very brief introduction to this topic, and also some very brief presentation about how to program them. So first of all, what is an agent? Or maybe we can start by saying what is not an agent. So an agent is not a program. So an agent is not something that takes some data as input, transforms it, and produce some data as the output. An agent is also not an expert system that starts from some knowledge, makes some inferences on top of it, and produces some knowledge as the output. The main idea of agency is to produce actions. So an agent is situated in an environment. It's a very important concept here. And this environment provides some perceptions to the agent, something the agent can see in its current environment. And the environment also allows the agent to perform some actions. So for instance, if we can take a very simple example, the mobile robot that is able to perceive its environment by means of its sensors, and it's able to act in this environment by means of some actuators, motors, and so on. But you can also think about a more softer agent that is capable to perceive some social media channels, decide something, and as the consequence, the action is to publish something in Twitter or something like that. So we can consider a very software-oriented agent where perception and actions are based on internet or something like that. In this video, however, we are not focusing on this general idea of agent, but we will focus on the idea of agent as it's conceived in artificial intelligence, especially by the proposal of Alan Newell in his paper, very important paper, where the title is The Knowledge Lab. In this kind of agent, the most important component is the knowledge. So an agent is an entity that behaves or that produces actions essentially based on what this entity knows, the knowledge. So the knowledge can be composed by several different kinds of elements, but it comes from perception or from developers or whatever, and is used for some deliberation process that decides what to do in this particular configuration of the environment. So the agent is an entity in this case that is continuously running a kind of loop. We call it reasoning cycle that has 3 steps. The first one, the agent does perception. It looks at the environment and see its current state and updates the knowledge base on top of it. So new knowledge can be obtained by perception or something the agent knows before is not known anymore. And then based on what the agent knows, there is a second step. That's a deliberation step where the agent decides what to do, what action to do in considering its current knowledge. And then it does that action and repeat this process. So in this sense, to program an agent is quite different than to program other kinds of entities or to program a computer. To program an agent is to define its knowledge. And when the agent has this knowledge, it's up to the agent to decide the sequence of actions that is more suitable for the current state of the environment and for the goals of the agent. So in some sense, we are giving some autonomy for the agent to decide the exact sequence of actions that should be performed. The developer is just giving general knowledge or know-how about the application, about the environment, and about how goals can be achieved. But it's up to the agent to select the actions and the sequence or the order of the actions to achieve some goals. So the knowledge of the agent, that is this main component, can come from different sources. The first one, as you saw in the previous slide, is the case where the knowledge comes from the environment in the perception process of the agent. So the agent knows something that is perceived in the environment. The second important source of knowledge of the agent is the knowledge that is provided by the developer. So the developer in general knows very well the application, the system, and especially the developer knows how to solve problems. And then he expresses his knowledge in some language and provide that knowledge to the agent, especially know-how knowledge about how goals can be achieved. But knowledge can also come from other agents in the case where they are communicating and exchanging knowledge or sharing knowledge about the current state of the environment or even about how to achieve goals. And of course, the knowledge can come from the agent itself in the case where the agent is able to perform some reasoning or some inferences or even some learning. To illustrate how systems can be developed using this agent approach, we will consider in this video a smart room scenario. In this case, we want to develop a system that controls the temperature of some room as desired by some user. And so the environment is this room, and the agent is situated there to change the current temperature to the desired one. And this room is also equipped with a kind of air conditioner that the agent can use to control the temperature, to increase it or to decrease it. And this air conditioner has two main components. The first one is it has a sensor that captures the current temperature and make this information available to the agent. And the second is a set of operations the agent can start, like start cooling, heating, or stop the air condition. To design this system, we are following a very important principle related to the separation of the concern. So there is one part of the system that is concerned about how to interoperate with this air conditioner and the hardware and protocols and this kind of stuff. And this part is more related to how the environment is conceived and how it is implemented. And the second part is more concerned about how the agent decides its actions in this application. It's related to the strategy to keep the room in the desired temperature. The first one is more related to the environment, while the second is more related to the agent design. So this picture tries to detail a bit this design. So we have an agent, we call it room controller, and this agent has some goals related to the current temperature. And this agent can use some part of the environment, and here this represents an artifact of the environment, and this artifact has three operations: start cooling, heating, and stop, and provides two information to the agent: the current temperature and the current state of the environment. We call these two elements here observable properties of this artifact, and these three elements here are three operations that are exposed in this environment for the agent. So from the agent side, we can see that this agent has a perception: the current temperature, should do some deliberation, and as the output of this deliberation decides some actions that are available: start cooling or heating, and stop the air conditioning. And the knowledge of this agent is essentially based on temperature: the current state of the temperature, the desired state of the temperature, and how to act in order to achieve some goals. So let's go and try to see in more details how this knowledge can be specified for the agent. Here we are using the JaCaMo language to program the application, both the environment and the agent. And here the focus is on the agent. And in this programming language, the knowledge has three main components: beliefs, goals, and plans. So what are beliefs? Beliefs are information the agent has about the environment or the agent itself, etc. And it's represented using this syntax. Is very inspired by Prolog and logic programming, where you have a predicate, temperature, and some arguments. In this case, to say that the current temperature is 20 degrees. So if this information is in the knowledge base of the agent as a belief, it means that the agent believes that the current temperature is 20, possibly because of perception. The second element of the knowledge base of the agent is its goals. So in this case, for instance, the agent has the goal that the current temperature becomes 20. So the syntax is very similar to beliefs, but we have this exclamation mark before the name of the predicate. So it means not the current state, but the desired state of the environment. In some sense, an environment where the temperature is 20 degrees. And the third component of the knowledge base of the agent are plans, and they are very, very important in JaCaMo. And they are used to specify how goals can be achieved by actions, of course. So this is how we can write a plan. It has two main components: what triggers the plan and what to do in response to that event. So it represents an event. In this case, the event is I start having the goal that the temperature is 20. And to achieve this goal, I do this action, start cooling. So it's the know-how about how to solve problems in that application. And a plan is, again, an event and a sequence of actions. And plan can also use to implement some reactions to changes in the current state of the environment. So for instance, this event represents the fact that the agent started to believe that the current temperature is 10. So there is no exclamation mark here. So it's a new belief. The plus means a new belief, temperature is 10. And here is how the agent could react to that event. In that case, it's not by doing an action, but by creating a new goal. So as soon or whenever the agent discovers that the current temperature is 10, he creates the goal to set the temperature as 20. Let's see how we can implement this kind of application in JaCaMo. Of course, the idea here is just to give a very general idea of how we can implement this kind of system and not present all the details of this language or the JaCaMo platform and so on. We will produce other videos for that. So every JaCaMo project has a GCM file where the main components of the project are described. So in this case, for the smart room multi-agent system, we have one agent called RC, and we have an environment where the room is specified. In this environment, we have the air conditioner, or here an implementation of a simulator of the air conditioner where the initial temperature is 30. So we are using a simulator here to play a bit, but our focus is on the agent side. So this agent program, in some sense, is specified in this file, and the agent is situated in this room and looking to perceiving the air conditioner. So what is the code of this agent? So the file is this one. So the most important is the first two lines that consists of two plans. The first one is whenever the agent perceives that current temperature is 30, that it's the case initially because we start the simulation of the environment is temperature is 30. So that belief will be the case for the agent, creates this goal. And to achieve this goal, the agent executes the action start cooling. So very, very simple. Now you can start thinking or imagining how is the behavior of this agent. So if try to see what's the result of the execution, I run it here in this console, and we will see that the agent start cooling, and then the temperature of the room starts decreasing. Of course, it is a bit a simulation, but the agent perceives the temperature as 30 and then executed the action start cooling, and the environment start cooling forever. Of course, this is not a good program. The agent should execute stop air conditioner in some situation. In that case, let's suppose a very simple case. Let me copy from somewhere. So we have a third plan. If the agent perceives the current temperature as 20, the target temperature, it executes the action stop the air conditioner. So if I execute the application now, we have the temperature decreasing until 20. So it's quite okay. This initial implementation of the agent is, of course, not a good implementation. It's very simple, but is not good enough. For instance, if the initial temperature is not 30, but for instance 35, and then this plan is not executed, and so the agent does nothing. If I run it again, we will just see that there is some problems here during the execution. Just to say that this plan is not triggered, the goal is not created, and the agent is not start cooling just because the initial temperature is another value. So it's not a good program. But before going on and trying to solve this problem, let's just to say something about the reasoning cycle of this agent. That's a bit more detailed than the general reasoning cycle presented in the first slides. Of course, the main steps are still there. The agent starts doing perception, in this very particular case, perceiving the current temperature, and this cycle ends by doing some actions that are coded like this. And but in the middle, the deliberation part is more detailed in JaCaMo interpreter. The main steps are the following. Any change in the knowledge base of the agent, it could be changes in the beliefs or changes in the goals, you produce events. Events are represented here by the plus signal. And then at every cycle, there are some events to be handled, and the agent will select plans for handling those events. So if there is an event like this plan is selected. If there is an event like this one, a new goal, this plan can be selected. And then after the plan is selected, the plan is executed by creating a goal in this case, or by doing an action in this case. So let's see a second version of this agent. Now the agent has 4 plans. The first one is a copy from the previous version, where if the agent believes that the current temperature is 20, that's the target temperature, it stops the air conditioner. If the agent perceives some other temperature, T is a variable, so anything different from 20, the agent creates this goal. So we have here 2 plans for the same event or same kind of event. If the event is temperature 20, the first plan is used, otherwise the second plan is used. And then to achieve this goal, we have now 2 plans. The first one is, if I have the goal of setting some temperature Dt, and the current temperature is T, and it is greater than the desired temperature, then execute start cooling. If I have the same goal, believe that the temperature is some value T that is less than the desired, then I start heating. So in this case, the agent is able to either start cooling or heating, and between the decision between the 2 actions is done by these conditions here. So this is new in the syntax of plan. So a plan has an event that triggers its execution and a context that defines where this plan is suitable. So in this case, the agent can choose one or another, and the decision is based on the current temperature. It's based on a belief. So if we execute this second version of our agent, we have the initial temperature as 30, and then the agent does start cooling, and until the temperature goes to 20. But if the initial temperature is, for instance, is not 30 but 10, and you execute it again, instead of start cooling, the agent will execute start heating, and then the temperature again goes to 20. The main issue about this implementation is that now the agent is running, but what happens if the current temperature changes? So we have a the cooler here just to change the current temperature again to 30. So it goes back to the agent reacts to that change in environment, setting up the temperature again. If the current temperature by any chance goes to 10, the agent reacts to that, start heating. So the agent, although in this moment we don't see any action, he is still running, And as soon as he perceives that the temperature is T and T is not 20, he creates this goal. So the agent is in some sense reactive to changes in its current environment. One problem with this implementation is that 20 is fixed here. The target temperature is fixed in two parts of the code. And so if we wanted to use another value, we have to remember to change in two places. So it's not a very good implementation. So we have a third version of this agent where the agent has an initial belief set by the developer, where this belief represents the desired or the preference temperature for that room. And then the plans that creates the new goal, it's a bit different. We have a variable here. So if the current temperature of the environment is T and the preference is P, and there is some difference between these two values, then creates a new goal. And whenever the agent perceives temperature as T, and T is also the preference, so the current temperature and the preference are the same T, then it stops the air conditioning. So now the preference is here, and we can change it quite easily. Let's run it just to see how this agent works. So we use the version 3, and when I run the agent, I guess I didn't solve this. So let's run it again. So it works. And then if I change the current temperature in the room to 30, the agent also reacts. So this is still an agent that is able to react promptly to changes in the current temperature. And of course, it's quite easy to change this belief to another value, just to change this and run it again. So the preference is one. I will not show the example, I will not run it here, but this belief can come from the user in some sense, from other agents and so on. So by simply changing this belief, we are changing the desired target temperature. So this agent implemented by these 4 plans and this initial belief, it's an agent that we can classify it as a very reactive agent, because what he is doing is to react to changes in the current temperature. And to achieve some goal, it's simply doing an action. So the agent perceives the environment, select an action, and stop doing anything until some new temperature is perceived. So it's a kind of reactive agent, or a reactive style of coding an agent, reacting to events. Another usual way to develop agents is to create a kind of maintenance goal. In this case, the agent is not reacting to the environment as before, but the agent has one goal, initial goal in this case, and the goal is this agent defined by the developer. And so the goal is created as soon as the agent starts executing. And to achieve this goal, the agent has 3 plans. The first one, if I have this goal, and current temperature is T, that is different than the preferred temperature, then does the action start cooling. But, and here the most important part, keeps the goal of keep temperature. So the goal is maintained in some sense. The agent does this action and tries the goal again. It's a kind of loop in some sense. It may be to achieve this goal. This plan is a candidate again, and then maybe the temperature is different and it does another actions. For instance, this case here, that the temperature becomes less than the preferred temperature and the air conditioner is not in idle, then does stop air conditioner. The start heating is removed from the scope. So there are three cases. Either the current temperature is higher than the preferred, then start cooling. The current temperature is equals or below the preferred, in that case it stops. And there is a third case where the agent does nothing, just wait a bit and try to go again. So in this agent, the goal keep temperature is always in execution in some sense. From the behavior point of view, there is not a big difference. So the agent runs as the agent before, but in this case, the agent has always a goal, and all the actions, in some sense, are a result of this goal that it's always running. One advantage of this solution is that even if I change the belief preference while the agent is running, since this keep temperature is a kind of a loop maintenance goal, the agent will react also to that. So the agent will react to changes in the current temperature or in the preference, because he is testing these conditions every reasoning cycle. We have finished to implement this agent using this approach based on the JaCaMo platform. What we can highlight and notice about this source code, especially considering or revisiting the concepts and ideas presented before. So the first thing is that we have a clear separation between the environment and the agent, or how this software is integrated with the hardware, the air conditioner, and how the strategy to set the current temperature in a desired value is implemented. So we are mainly focusing here on how to decide what to do in terms of the current state of the environment. But the environment itself is seen here by beliefs like temperature and actions like stop air conditioner. From the agent developer perspective, we don't need to be worried too much about how this action identified here by this string is really implemented, how to connect the air conditioner and so on. We also don't need to be worried about how this belief comes to the agent mind and how often it's updated and how and so on. If we see another tool that JaCaMo provides is called Agent Mind Inspector. So we can see the mind of this agent. In this case, we are looking at his beliefs, and we can see here, especially these two beliefs, the current state of the air conditioner and the current temperature. These two beliefs are updated automatically by the platform and how it's taught. However, this belief was inserted by the agent developer. So another important aspect of this agent is its source code. It's not a sequence of actions like begin, do something, test something, and then execute something. This source code is mainly a sequence of declared plans where the developer wrote in this particular language his knowledge about the application, and especially his knowledge about how to act in order to achieve some goal. So the source, you can see in the source code, beliefs, goals, and plans. So the source code is in the end knowledge represented in that language, knowledge about beliefs, goals, and plans. So let's wrap up. What are the main features of this kind of agent? First of all, they are reactive. Since they are always executing a reasoning cycle and perceiving the environment, as soon as the environment changes, he can react to that. So agents are very reactive to the environment where they are situated. But they are also proactive in the sense that they are doing actions to achieve some goals. And this proactive can also consider long-term goals. So the agent may have goals that takes quite a long to be achieved, as in the example, the keep temperature goal. So the agent may have goals and doing actions for a long time to achieve them. And usually it's not so easy to develop systems that are both reactive and long-term and have long-term goals. It's quite easy to develop systems that are only reactive or only long-term oriented, but to having both features is quite difficult to combine. And this kind of agents we presented in this video are very strong on that. Agents are also context aware in the sense that they are, again, perceiving its environment and selecting plans accordingly. So if the environment changes, other plans can be changed. In that sense, as said in the beginning, the developer is not defining the exact sequence of actions that should be performed, but they are declaring conditions for the actions to be executed. And then it's up to the agent to make the best selection of actions. I didn't explore very in detail this aspect of agents, but transparency is quite easy to see. For every action that an agent performed, you can always ask the agent why you did that action, and the agent is able to answer, at least in terms of its beliefs and goals, the reasons for the actions. And also not very well explored in this video, maybe in future videos we can go further in that details, is that these agents are founded in very good background works. For instance, the practical reasoning, I mean, the ideas of reasoning for actions that comes from many philosophers, but in this case, especially Michael Bratman was a huge inspiration for how practical reasoning is implemented in these languages. Also the idea of intentions and the PDI architecture that's where JaCaMo is also inspired. This architecture that's three main components of the knowledge: beliefs, desire, and intentions. Regarding the agent part of the JaCaMo platform, it's based on a language specific for agents called JSON. And in this book, you can find a lot of information and details about how to program agents using the JSON language.